and we'll get started. Good morning, everyone. Welcome to our SUR seminar here today on Friday morning. Today, it's a great honor to have Dr. Hamid Rahimian from Department of Industry Engineering, Clemson University, to join us for the seminar. Dr. Rahimian is an assistant professor at Clemson University. Before joining there, he was a postdoc research fellow in the Department of Industry, Engineering, and Management Science at Northwestern University, and he obtained his PhD in operations research from the Ohio State University. Dr. Rahimian is broadly interested in data-driven decision-making and uncertainty by combining ideas from optimization and statistical learning theory to develop new theory tools, algorithms with applications in scarce data sources, allocation in complex, uncertain environments, and incomplete information. His work has focused on problems in engineering like water and energy, and operations in terms of healthcare and inventory. His research has been well recognized by the runner-up prize in 2017 in the Informed Computer Society's Student Paper Award, and also won a second place prize in 2019 IISE Doctor Dissertation Award here. So today he will be presenting contextual trans-constraint programming. Welcome, Hamid, and please. Thank you.
Thank you so much, Rand, for the very kind introduction. And of course, the invitation. It's my honor to present my work at your seminar series. Good morning, everyone. As Rand mentioned, I'm going to talk about contextual trans-constraint programming. This is a joint work with my colleague, Bernardo Pagnageli from Universidad Adolfo Ibáñez in Santiago. All right, so I'm going to spend a little bit of time to explain the title of the work, trans-constraint programming and contextual trans-constraint programming. I'm going to formally introduce the framework. I'm going to present some theoretical and numerical results, and finally wrap up with some conclusion and paths for future work. Let me start by introducing classical trans-constraint programming. I know so many people in this call are familiar with trans-constraint programming, but let me take my time to a little bit elaborate on this context, especially if you are from other areas or discipline. Classical trans-constraint program, it's a popular method for decision-making under uncertainty, where essentially the goal is to come up with some plan or design for a system that is subject to randomness. In fact, suppose that you have some constraint, physical constraint or logical constraint in the system that are being perturbed by some random parameters, and instead of satisfying all those constraints for all possible realization that your random parameters can get, you want to satisfy them with a high probability. Formally, let's suppose that you have a decision vector U that sits in some feasible region, capital U. You have your random parameters of interest, which are the uncertain parameters in your model, which is a random vector. And you have a joint probability distribution that is governing the distribution of your random parameters. You want to minimize some objective function as a function of your decisions, where you want to satisfy the constraint in the model, this generic form of G as a function of your decision on uncertain parameters to be less than or equal to 0, let's say, in a generic form, and you want this constraint to be satisfied with a high probability, where the probability is taken with respect to this true probability distribution, and you want to satisfy this constraint with a high probability where this parameter alpha is controlling the conservatism of the decision maker. The higher the 1 minus alpha is, the closer the model is to the case that you would satisfy all constraints for all possible realization of the random parameters. This is a well-studied problem, not only in the optimization, at least, in fact, if you look at the focus on the constraint part of the problem, which is something that is referred to chance constraint, this is also well-studied. In fact, the left-hand side is well-studied in other domains. In probability and statistics, people are usually interested in obtaining or calculating the probability of having some random vector sit in some set, and that's in fact something that people refer to as uncertain quantification, and that's exactly the thing that appears in the left-hand side of a chance constraint problem. So if you are from those domains, I hope this is familiar framework. We just do an optimization over this setting. Let me introduce some applications where chance constraint programming can be useful. The applications are abundant, from healthcare to engineering to cyber physical systems to finance. There are numerous applications of chance constraint programming. I'm going to mention a few of these applications to sort of prepare you for what comes later. Let me focus first on the problem that arise in farming or agriculture. Suppose that you want to come up with a plan to decide what portion of a farm to plant, let's say soybean and corn, in order to have a total yield of certain number with a high probability, where the thing that is random in this setting is the crop's yield. You're not sure about the yields of the crops, and you want to have a chance constraint program to take care of this uncertainty, and you want to satisfy that target constraint with a high probability. In a financial portfolio optimization problem, you can also think of similar setting where you want to make a decision, let's say for your retirement in the next 20, 30 years, you want to make a decision on how much of your money or proportion of your money should be allocated to different indices in order to have a total cumulative return hitting some target with a high probability, where again, the returns of your assets that you want to decide on choosing as part of your portfolio is random. These are just two applications, but let me give you some perhaps more applications if you are working some other application domains. Let's say you want to come up with a plan or make a decision on the capacity of some healthcare facilities, some hospitals or operating room, so that you would admit the patient's arrival to the system with a high probability. Or you can think of designing capacity for a call center where you want to respond to the calls with a high probability. You don't want to drop the calls. In a network design problem, perhaps you want to get from point A to point B, and you want the cost, whatever that means, of reaching from origin to the destination to be smaller than some target with a high probability. You can think of applications in energy, power system, and so on and so forth. So what I'd like to ask you is to pick one application, whatever application that you are more comfortable with. And as I walk you through the presentation, you can try to make the connection between the things that I mentioned and the area that you are most familiar and comfortable with. If you like, you can also, I'm going to stick to the finance, at least a stylus finance application problem. You're welcome to follow my application as well. All right, let's think a little bit, talk a little bit about how to handle the chance constraint programming and what are the challenges of dealing with this problem. If you pay attention to the left-hand side of the chance constraint, in fact, you are calculating the probability, right? In fact, we need to calculate or have some multidimensional integral, and we need to calculate those probabilities using these multidimensional integrals. And not only calculating those probabilities, but also we need to do optimization on top of that. So this is it's not easy to, in fact, realize that this is not an easy thing to do, even especially if you have multidimensional random variables, and it can get real intractable real quick. Special cases that you can handle are very rare. And in a general sense, this is very complicated to handle. On top of that, you might not know the probability distribution that govern the random parameters with certainty. Instead, you might have access to a data set of historical data. Let's say you have a data set of n data points where you have observations of the random parameter of interest, psi. And perhaps you can form an empirical probability distribution using your data set and replace the true probability distribution with this empirical probability distribution that I denote with P superscript n. And we know from basic probability theory that we can write this probability using an indicator function where we will have this expected value, where the expected value of the indicator function is taken with respect to the empirical probability distribution. And this is nothing just the arithmetic mean of the indicator function, where I will assign a weight of 1/n to each data point, right? And I want this arithmetic mean to be satisfied, to be larger than 1 minus alpha, the tolerance that I would consider for the problem. And just again, notation, this one, bold one is nothing, just the indicator function of negative numbers, where the indicator function is 1 when g is less than or equal to 0 and 0 otherwise. Right, this is one approximation for handling the chance constraint, something that in the literature is referred to as sample average approximation. This is not the only approximation that you can do for chance constraint programs. In fact, other approximations have also been studied, some of them by the people in this call. Properties of this approximation has been studied in terms of consistency and rates of convergence. People have looked at Monte Carlo sampling, convex or Bernoulli approximation, conditional value at risk approximation, distribution robust optimization approximation. They're all well studied and well understood in terms of consistency and rates of convergence in the literature. However, there is a piece that is missing in all of these studies, especially in today's data-rich world, where we continuously collecting information about the things that are happening around us. For instance, you can use sensors in cyber physical system to collect information. You have access to social media, e-commerce, and so on and so forth to collect something that people in the statistics refer to as independent variables, covariates, features, or attributes, or contextual information, something that is attached to or comes with the random parameter of interest that you have, psi. And this is something that not only you are collecting, but also at the time of decision making, you would have access to those information. Perhaps you would have access to new observation of these features, and perhaps you can use those information at the time of decision making. In the classical chance constraint program, this contextual information is either totally ignored or it is encapsulated in the psi by just enlarging the dimension of the random variables, just attaching psi to the covariates and just follow the path of classical stochastic program over an augmented random variables. So what I'm going to talk in the rest of the talk is about how to handle classical, how to in fact augment classical chance constraint program and use contextual information and have a framework that take care of those information so that we can make smarter and more intelligent decisions. Let me bring back the applications that I mentioned earlier in the talk. In the farming, in the agriculture example that I mentioned, you can think of contextual information, the site information, as the weather parameters. Perhaps precipitations, humidity parameters can be something that you need to take care of and think about and take into account when you are thinking about the crop's yield, because these factors would affect the crop's yield. You can also think about the type of the pesticides that you have used in the past or the type of pesticides that you're going to use when you're making the decision today. In the financial portfolio optimization problem, you can also think about some contextual or auxiliary informations, perhaps gathered from Google searches, social media, things like unemployment rate, real estate prices, political comments that are made by politicians, oil prices, and things like that. If you remember a few months ago, what happened to GameStop, the things that happened in social media and Reddit, those kind of information are the information that you have available to you. We are collecting them continuously, and why not using them while we are making decisions? All right, with this sort of lengthy introduction and motivation, I hope that everyone agrees that we have access to this information, and at the time of decision making, we can take advantage of this information. So now let me introduce how we can incorporate this contextual information in the classical chance constraint programs. The way that we're gonna do that is assuming that I have observed a new covariate vector of the random capital X. Let's say I have observed this little x as my new observed covariate realization, I'm going to think about what's going to happen to the optimization problem if I'm given with this information. And when I say given, you can immediately think about conditional on the new observed covariate information. And because I'm dealing with the probabilities, you can think about, you can in fact think about conditional probability distribution, because psi and x are depending on each other, and you have a joint probability distribution over them. When you are given the new covariate vector, you can think about the conditional probability distribution of psi given x. And when you look at the chance constraint, you can think about the conditional probability distribution. You want to satisfy the chance constraint conditioned on the fact that you have observed this little x, which is your new covariate vector. And still you want to satisfy this chance constraint with a high probability. And you can observe that this problem is being parameterized by this little x. The optimal value is going to depend on little x, and whatever solution that you will have also going to depend on the lower x. In fact, you will have a mapping at the end of the day from the feature space to the decision space, forming the optimal solution or the set of optimal solution to this problem. So this is the framework of the contextual chance constraint program. Some people sometimes refer to it as conditional problem. And by that, we mean that we are looking at the conditional probability distribution. So what are the challenges to work with this problem? This is a nice framework. It makes things to take advantage of this new covariates information that we have. But as before, again, we have to deal with multidimensional integrals. And as before, we might not know the probability distribution. Here, the probability distribution is the joint probability distribution of covariates and random parameters. And because we cannot know that for certain, with certainty, of course, we cannot know the conditional probability distribution of psi given x. However, as before, we might have some historical data available to us where now our observations are augmented with this components of the features that we have observed in the past, and they are now forming a pair of random variables of features and a random parameter of interest. And let's say you have a data set of size n, and you want to make advantage of this historical data when you are making decision, when you have a new covariate vector x, and you want to still make a decision u to minimize that objective function. Still the psi is uncertain, but perhaps you can do more in this setup compared to the classical chance constraint program. Now let me, in fact, work with this simple portfolio optimization problem where I'm going to make a decision on how much to invest on two assets, stocks and bonds, where the returns of the products, of the assets are uncertain, and I want to maximize the return, and I want to get to this maximum return by satisfying to this constraint to have a return, a cumulative return of reaching some target value. Let's say I have some nominal values for the returns of stocks and bonds, a two-dimensional vector. I have some target value that I want to reach. My target is 0.8 return. I have a tolerance level of 10%. And the feasible region of this problem is nothing but just a simplex in 2D, right? So I want to make decisions in the sense that the total investment sums to 1 in terms of the proportion. Let us suppose that the returns, this random vector of return 1 plus psi, is a multivariate normal distribution with some nominal mean. And I have a covariate matrix that now depends on the features. In this setup, in this example, the feature is a univariate random variable. It takes only values of 0 and 1. And it is, this covariate is in a way that the off-diagonal elements for both cases, for both x equal to 0 and 1 are the same. However, the diagonal elements, the variance of the assets returns are higher when we are in the case of x equal to 1. So in fact, we are more volatile in this case, and you can think of x equal to 1, indicating some bad market situation or volatile market situation, whereas x equal to 0, it's some sort of regular market situation. So I'm going to work with this problem and do some experiments on that. Let's say first I want to handle this problem with a classical SAA approach. Let us sample 10,000 samples from that multivariate normal distribution. Half of the samples are coming from the case that x equal to 0, good market situation, and the other half from the case that we are in a bad market situation. Now I want to use data, these 10,000 samples, and I want to totally ignore where they're coming from. I'm going to totally ignore that whatever the feature that is associated with this observation, totally agnostic with respect to the features. When I do solve the optimization problem using classical SAA, I will see that I'm going to invest 58% of my money on the first asset and the remaining on the other one, and I would get a return of almost 1%. So this is my in-sample solution that I got from SAA. And once I get this solution, and if you tell me, hey, we are in the situation that we are, that the market situation is good, it's a regular situation, you can see immediately that this SAA solution that you observed and you calculate is in fact feasible to that contextual problem. Whereas when x equal to 1 and you are in a bad market situation, you can see that this solution is no longer feasible to the chance constraint. In fact, you're not satisfying that chance constraint, and this solution is no longer implementable for a contextual problem. So ignoring the contextual information lead to some undesirable situations for us. So the question is how we can leverage this information, this contextual information, along with the information of the new covariate vector that we have, and use those information in our favor so that this type of situation wouldn't happen. Let me explain a little bit about this stylized problem. I'm sure that you might have some problems, and you make a suggestion. All right, so I accept that ignoring contextual information is bad, and I'm going to make a suggestion. Why don't you you solve the case when x is equal to 0, this contextual problem, by only focusing on the half of the samples that have x equal to 0 attached to them, and do your optimization problem sort of conditional based on this x equal to 0. You would have a SAA using 5,000 samples, and you come up with some solution. Maybe there are some hopes. This is a valid question and suggestion, but let me answer that in a way that in this problem, I only had a univariate covariate vector, covariate random variable that had only 2 possibilities. In practice, you might think of a situation that you have hundreds, thousands of realization for your covariate, even this univariate covariate vector, covariate random variable, and it might not be the case that you even observed in your historical data, let's say x equal to 0. So with that approach, I cannot even come up with some samples that have x equal to 0 attached to them, and I cannot do or perform the optimization using that conditional suggestion that you had. And not only that, I might have in many situations have to deal with the case that this univariate random variable of this feature would be continuous. And I would know that with the probability 0, it is impossible to observe x equal to 0 or x equal to 1 or any other number in my historical data. And on top of all of this, we usually deal with the situation that this covariate vector is multidimensional. I don't want to say high dimensional, but at least multidimensional. And again, these all sort of challenges might happen, and conditioning the samples based on the covariates, just doing the regular SAA might not work. So we need something that is smarter and takes advantage of all the possible information that and historical data that we have, not only those that have the same components of feature, the same as the new one, but also we want to take advantage of all the other observations that possibly were observed using other feature vectors. All right, let me now talk about how people have dealt with contextual information in the context of stochastic programming. This is an emerging topic in stochastic programming. One approach is using the so-called empirical risk minimization approach, where essentially you come up with a map that map your feature space to the solution space. This approach is parametric, something that perhaps we can think about people doing regression analysis. You feed a model using your historical data, and whatever new feature attribute you give me, we can spit out the prediction of the model. So you can think of this approach in the same manner, but we are here making decisions. So we're gonna come up with some decision rules and restrict ourselves to some decision rules and come up with this solution map. The other approach that people have aimed for is aiming for learning the random parameters given the features. This approach pretty much work in a way that you aim for a better predictive model, you feed the model using your historical data, and then you sample from that feeded model and use the classical SAA using those sampled observations. The other approach is to aim for learning the distribution of psi given X, because at the end of the day, I would care about the probability distribution of psi given X, and why not aim for a better probability distribution estimation for this, and this is where our work also belongs to. I'm going to elaborate a little bit on how to aim for a better estimation of this conditional probability distribution. I know that ideally I'm looking for a probability distribution, a conditional probability distribution that would converge to the true probability distribution with probability 1. That's the ideal situation that I'd like to have, and the way that we suggest to estimate this probability distribution is as follows. As before, I'm going to sort of have the empirical distribution mindset. If you remember, in the classical SAA, I would allocate a weight of, a weight of 1 over n to each possible realizations. Now, instead of giving a uniform weight to all possible realization, I'm going to allocate to each realization a weight that depends not only on the observations, but also on the new feature vector that I have observed, this little x. So this way, perhaps some realization can get a higher probability, whereas some other realization might get a lower probability. And of course, because this is a probability distribution, the sum of these weights, Wi, as a function of x is going to sum to 1. Now, if I use this new probability distribution, I can form this data-driven contextual chance constraint, whereas before I would use just this weighted average of the indicator functions, where now the weights are governed by this weights Wi as a function of x. Again, as classical SAA use the 1 over n weight, in fact, the arithmetic mean of the indicator function, whereas here we are not going to allocate a uniform weight to all possible realization in the hope that we would take advantage of the relationship between the ice observation and the new covariate vector. In order to come up with this weighting function, we rely on machine learning based approaches. One popular way is to use the so-called kernel functions, the celebrated Nadarya-Watson estimation, where essentially we would allocate a higher weight to a realization that would have a higher similarity to the observed covariate vector x. For instance, if I use the so-called Gaussian kernel, where I look at the norm between this vector, the difference between x, the new vector x, and observed vector xi, the larger this norm is, I would allocate a lower weight to this observation, meaning that it's far from what I have observed, so I rather to allocate a smaller weight to this observation. Whereas if the featured vector x is closer in some sense to the ice observation, I would rather to allocate a higher weight to this observation, hoping that this will make a better decision for the optimization problem. I can also think about other approaches like k nearest neighbor, where I allocate a 1 over k weight to the k nearest neighbor of the observed vector x. I can think of classification and regression trees, where essentially we allocate a uniform weight to all the samples that belong to the same leaf node as the one that the current vector x would belong to. We can also think about ensembles of this cart, random forests, where essentially you can average over different trees. All right, so this is about the construction, how to approximate this chance constraint using this data-driven approach. But the main question is, what is the effect of this approximation on the optimization? In fact, on the optimal solution that you obtain. Let us have a recap one more time. So the true chance constraint problem, if I knew the true probability distribution would be formed as the expected value of the indicator function. This approximated contextual chance constraint would be nothing but the weighted average of the indicator function, where the weights is being governed by this weighting function, which not only depends on the ice observation, but also on the random vector x that I have observed. And of course, using this approximation, the feasible region of the problem is going to change. Let us assume that the true feasible region is denoted by this U subscript alpha. This is the true feasible region, whereas the feasible region of this approximated problem is going to get this form, and I'm going to denote this by U subscript alpha, but I'm going to put a superscript of n, denoting that this is a data-driven approximation. Now, the main question is, what is the relationship between the feasible region that I get from the approximated chance constraint and the feasible region of the true problem? In fact, I'm interested in the probability of having a 1 minus gamma feasible solution to the approximated problem to be 1 minus alpha feasible to the true problem. I'm interested in that probability. And if I can have answer to this question, I can also answer and come up with some finite sample size in order to have a confidence about this probabilistic containment, about this probabilistic statement, so that I can satisfy this containment with a high probability, with a probability of at least, let's say, 1 minus delta, which is my confidence level. So now I'm going to spend some time explaining about these theoretical results. And in order to come up with the results, we use large deviation theory for a random weighted sum of random variables, which is different from the classical approaches that people in classical chance constraint program use. People usually use Coefficient type of inequality or Cramer's theorem to come up or to answer to these questions, because we have two sets of random variables here. Both the weights are random and also the indicator functions are random. We need to do something more, and we need to rely on some other results in large deviation. So I'm going to present and provide some insights about the theoretical results here. In the first result, I'm going to focus on the case that the feasible region, capital U, is finite, perhaps a discrete optimization problem. Then for some choice of gamma, I can say with a high probability, the approximated feasible region is going to be contained in the true probability region with a high probability, and that probability is going to go to 1 exponentially fast. And this guy here is the rate function, something similar to the results that people have observed in classical chance constraint. You have a rate function coming from the large deviation results. It has some expression. I'm not going to get into the details of how these rate functions are obtained or whether these functions are, but it has a similar flavor as the classical chance constraint program. And because I have this result on the top, I can now obtain a finite sample guarantees with a high confidence to make sure feasibility of the approximated solution to the true problem. And that's the expression that I would get at the bottom. It's written for having this feasibility guarantee. And if you're familiar with the classical result in chance constraint programming, a term like this also appears in those results. However, with the power of 2, meaning that for values of gamma that are sufficiently close to alpha, the number of sample points is going to grow faster. And also the dependency of delta to this power here, it appears with the roots, the R's root here, which is again different in some sense, different from the classical results. You don't have this power in the classical result because R in the setting is between R0 and 1. Again, means that in the classical chance constraint program, you would need a larger number of samples, as opposed to the one that you would get from the contextual problem, which is something that would make sense. Here we are using contextual information, and that the fact that we are using that contextual information is being rewarded by needing less number of samples in order to get the same or similar guarantees. The result can also be extended to the case that we have an infinite feasible region, but bounded, but perhaps by adding extra restrictions on the functions that governs the constraint, the G function. If I assume they are Lipschitz continuous, and I have some diameter on this feasible region, I can again get similar results to the classical chance constraint program, where again this parameter lambda, L, the Lipschitz constant, and D, the diameter of the set, appears in the result. And again, they have the similar flavor. The dependency of alpha and gamma, again, is similar to the results in the classical chance constraint. Again, this is appearing with the power of 1, whereas power of 2 in the classical results. And the dependency between the confidence and the powers or the roots, the R's root, is also similar to the previous results. All right, so now let me talk a little bit about some application. This is the end of the theoretical results that I wanted to mention. At least in this talk, we have some other results for some other cases, for special cases of the distribution, but let me not go into the details of those results. They all have similar flavors. Now let me introduce the problem that we consider to look into. This is a team composition problem in the context of a sports team. At the beginning of a season, a team has a roster formed by players that have active contracts. And the team has a series of target players that it would consider buying or borrowing from the other teams. You want to come up with the next season's roster, make decisions on buying, selling players, lending them out, borrowing them from other teams. And the thing that is random here is the future market value of the players. And we know this future market value of the players depends on the current market value, the age of the player, and the technical role or position that the player has in the team. Perhaps in the context of basketball, we can think of roles like shooting guard, pointing guard, and things like that. And the objective of the team manager is to maximize the team's performance, quantified by some ratings, and also at the same time, it's some chance constraint on the future market value of the player. So we have also some financial restriction that we need to take care of. Don't want to get to the details of the mathematical formulation, just I'm going to showing it to show how simple the model is, but it captures some main features of the problem. I have some restrictions on the number of players in the whole roster, the number of players in each role. I have some budget constraints, and more importantly, I'm having this chance constraint. This is highlighted one for the future market value of the players. The objective function is, as I said, maximizing the ratings or performance of the team. And because I have a chance constraint, you can think of a balance between the ratings and the future market value of the player. Of course, I have the flexibility over my chance constraint by controlling this tolerance level. For instance, again, in the context of basketball, if you are, let's say, Chicago Bulls 91 to 98, you can think of considering an objective function that doesn't care much about the rating of the players because you are having the best players in the league, and you would, you wouldn't care much about the future market value of the players because your players are doing well, you have the best basketball players in the league, and you would care more about the performance of the team because you want to keep that momentum. So in this case, you would choose a smaller alpha. However, if you are perhaps Chicago Bulls 99, you are losing your players, you're rebuilding your team, you would care more about the future market value of the players because you want to have some financial perspective, and you would choose a smaller alpha so that you can have some guarantees on the future market value of the players. All right, so I explained the problem in the context of basketball, but this is not something that we did. We used data from the Premier League, the soccer tournament in UK. We look into the 20 teams playing in the season of 2013-2014 in order to plan for the next season. We solve each problem for each team in 4 different ways. We use CART in order to form the contextual chance constraint. We use random forest to form the approximated problem. We use SAA in a way that we considered the contextual information, but we assume that there is a parametric relationship between these dependent and independent variables. We feed a model, we sampled from the fitted model and just use a classical SAA. And the third and the last one is the one that I refer to as naive SAA, which is the one that totally ignores the contextual information. And for the numerical results here, I'm focused on feasibility in a similar sense that I explained for that simple portfolio optimization. If I obtain some feasible solution from the SAA approaches, I want to test whether they are in fact feasible or implementable or not. This is just a list of the players, if you're familiar with Premier League, just showing that. And this is some snapshot of a big part of the data that we have. As I said, we have the players, we have the positions that they play in, their age, the current market value, the season that this data is coming from, and the future market value. For instance, if I focus on the last player, Joe Cole, that's his role, 31 years old, current market value is £4 million, and 22.5 is the future market value predicted for the next year. And as I said, we use also CARD. This is again some snapshot to give you some idea how this works. So this is some tree that was formed. So in the first level, you are splitting based on the role of the players, and perhaps that player, Joe Cole, is belonging to this leaf node. So when I have Joe Cole in some of the teams and I want to come up with some approximation for him, I would look at all different observation that would belong to the same node or the same leaf node as Joe Cole would belong to, and I form my approximated chance constraint. And for all the people who are in the same leaf node, I will allocate uniform weight to them. All right, so in terms of the experiments, we'll look at different values for the tolerance level and this parameter rho, which shows the growth in the future market value. We look at 20 possible, 16 different possibilities here in this table. We look at the optimal in-sample optimal value of this optimization problem. We also look at the out-of-sample performance. In this table, wherever you see a dashed line, it means that the problem was infeasible, and wherever you see a value of 1, it means that this problem, this setting had the highest optimal value. All these values in the optimal value column are normalized to 1. And you can see that for the naive SAA, all the times for this particular team Chelsea, none of the problems setting configurations were feasible. The SAA were feasible half of the time almost, whereas CART and RF are feasible almost all the time. They do very well in sample. And you can also see this SAA approach, even though it sometimes gets you the best optimal value in sample, out of sample, it doesn't do well, and it doesn't satisfy the chance constraint. Similar situation would happen for the other teams. Again, some other team, Tottenham, again, in naive SAA, it's infeasible most of the time. Similar for SAA, half of the time. And again, CART and RF are doing well in terms of the objective function and feasibility. And this is a more summarized way of that feasibility and feasibility issues that happen. These are again some representative teams, and again you can see for the teams that are shown in this slide, the SAA approaches that ignores the contextual information or use contextual information, but in a parametric manner, they happen to be infeasible almost all the time out of the 16 configurations that we had, whereas CART and RF are doing very well in terms of feasibility as well. All right, with that, I'd like to conclude the talk. I discussed how to include and incorporate contextual information in a chance constraint program. We presented the consistency and finite sample analysis to ensure feasibility as the number of data points grows by relying on results on large deviation of the random weighted sum of random variables. The results were from UK's Premier League, and I believe the future work in this area are numerous. One area for future research can be considering the case that these weighting functions themselves are ambiguous, and perhaps consider an ambiguity set for these weighting functions, develop some distribution robust framework for the contextual chance constraint program. Can also think about multi-stage version of the chance constraint where you have the chance of making recourse decisions. In terms of applications, there are also numerous areas of research. I'm currently working on a portfolio optimization problems where we consider real-world contextual information similar to the factors that I mentioned earlier in the talk. And I believe there are also a large area, a wide area of research in other domains, including energy, power systems, optimal flow type problems, and so on and so forth. With that, I'd like to end the talk, and here's the link to the manuscript on optimization online, and I would be happy to answer any questions that you might have.
Thank you very much for the nice talk, Hamid. So is there any questions here? We can open the floor for any question. So if you have any questions, just unmute yourself and ask, please. Yes, please. Merv?
Hi, Matt.
Hello, Merv.
Good to see you. So thanks for the great talk, and hi,
Thank
everyone.
you for attending.
I was wondering about your n number of scenarios in your samples. So I was wondering like whether you analyze the tightness of the provided bounds. I was wondering like in practice, like do we need that bound, or like we can get much like very similar quality results with a much smaller n value?
So you mean about the numerical results or the theoretical results?
So I was wondering whether the theoretical bounds, for instance, you should choose n as at least that much so that you have this probabilistic guarantee for your approximation solutions.
Right.
But I was wondering, is that tight, or you can get really good results with high probability of feasibility?
That's a really good question. Unfortunately, similar situation as a classical chance constraint program that you would not get a tight number of samples also arises here. So and you can also imagine, because the results also have similar flavor, and you're also using the large deviation results, those bounds, they're known to be not tight. So you can imagine that if you use these results in order to obtain those bounds for the number of samples, the practical number of samples would not be as bad, whereas this new theoretical bounds are, I would say, a little bit loose. So similar situation happens. Yeah.
Which is probably good news, right? So
yes.
That shows that it could be more practical than what you expect.
True, absolutely. Or if we can work more on, on the probabilistic result that we rely on to and come up with some tighter bound for those large deviation, I mean, that would be rewarded in the theoretical results as well. But I was not, I mean, we could not find or come up with a better bound than the one that we got here.
Okay.
But that's a really good question. Thank you.
Did you compare the results that you got with decisions that teams actually made in terms of getting players?
So that's a really good question. This is for not for this work. In this work, we weren't much. I mean, although I mentioned the work in the context of a real problem, this soccer problem that in fact the people have looked into, we didn't focus much on the decisions. But that's a really good question, that to see how the composition is changing, whether you are not using the contextual information versus the case that you use contextual information. Hopefully in the future, I will be more focused on the application part, and I hopeful to get some insightful results from that part as well. So part of the, I mean, this is perhaps some odd problem to look into when you are doing some theoretical work and you look into some soccer problem. The reason that we chose this problem was the fact that we had access to this information in some other literature, and we decided to go with this application because we found some caveats in the current literature of a stochastic program, because this is an emerging topic. It's very hard to find contextual information for more, let's say, engineering problems in energy or power system. It's very hard to obtain those data sets, so we decided to go with this application. But as you said, this also have some potentials to get more detail on the application itself, but we did not.
Thanks, that's helpful. And kind of a follow-up or related question. So the decision that's being made, I mean, it's basically with respect to the future value of a player, right?
Right.
So it doesn't have anything to do with the value of a player to a particular team, like how that's
true. That's true. That's just exactly the things that we consider, at least in the chance constraint, the future market value of the player. The value of the player to the team is something that is quantified by the rating of the player, which is deterministic. We assume that's deterministic and only affect the objective function of the problem. But the thing that is deriving the chance constraint is just the future market value, which again, assume that it happened to depend on only 3 covariates: age, current market value, and the role of the player. Thank you so much. That's a great question. And both of them, yeah.
Are there any other questions? We have a few minutes more.
Can I ask one more if no one is
Sure.
asking?
Yeah, please.
So I also observed, Ahmet, that like, for instance, if you have the continuous recourse case, then for instance, if you have this branch and cut type of algorithms, they directly go through, right, with your setup, because you are just changing the probabilities based on your estimates.
Absolutely. That's the way that it is. In fact, it would go through. And I also want to mention that in this work, we didn't much develop or use more advanced results on solving the problem itself, because the problem already was simple to solve. So we just use linearization of those chance constraints using binary variables, and because this problem was manageable, we only focus on that. But absolutely, you can also have those results to be tailored to this problem.
Hardy, you raise your hand, please.
Yeah, I do have a question. So in the case study, what values of alpha did you use? I was just maybe I missed that.
Yeah, so we use this at least in these tables. These are the parameters, the choices that we use for the alpha. In fact, we looked at a range of different values of alpha, let's say from 0.1 to 0.8. And you also have some sort of continuity that happens in terms of the optimal value. Let's say from 0.1 to 0.5, we didn't see any change in the results, so we just chose one of them to present the results for.
So, and you counted the number of infeasibilities at some point, right?
That's true. Okay. And these are just for a single observation of the features. Okay. Yes.
Is there any reason you did not try 0.9, or it's just that?
We tested that 0.9. I believe in many cases, the numbers were so tight, or the problem's data were so tight, that would often make the problem infeasible already.
Okay.
So there was no way for the decision maker to have that much of confidence in the future market value of the player.
Okay.
Yeah, that's the reason that we didn't try it. I mean, we tried that, but it was hopeless.
Feasible. Okay. Okay. Thank you.
Sure, absolutely.
Is there any other question? We can have maybe one more question here. All right, I think if there's no more questions, it's about time to conclude. Again, thank you very much, Hamid, for giving a really nice presentation, for joining us at the seminar here today. And if everyone here has a camera, I may want to open your camera and give a round of applause for the nice presentation to Hamid.
Thank you so much. It was a pleasure to present my work here. And again, thanks so much for the invitation.
Yeah. Thank you very much for all attending this seminar, and well, I think we'll conclude here. Have a nice weekend, everyone, and Hamid, hopefully we'll meet in person in near future at the conference.
Yeah, hopefully. Have a good rest of your day. Thanks again. Bye.
Bye. Thank you very much.
Thank you for the nice talk.
Thank you.